excuse me, we assume an RLC series circuit with some source of EMF that's driving the circuit with some angular frequency omega, which we're going to assume is the natural frequency of the system. So we have this where there's a certain maximum, which is the certain maximum of the driving EMF, which is the amplitude of the EMF. And then we have a cosine of omega t plus some initial phase angle, in general phi naught. And we assume that the resulting current is equal to some current amplitude, I max, maximum current, multiplied by the sine of the quantity omega t plus phi 1. Now, it comes out of the differential equations in this situation that you will have a current of this nature. We start by assuming the current. So we assume this. We don't assume this. Okay, we don't know what the Emax is or anything. We just assume that when this happens, that the current is going to follow the same angular frequency. It's going to be a sine or cosine function. It's going to have a phase angle. It's going to have a certain maximum. So the question then is, what are the voltage drops across the resistor, across the inductor, and across the capacitor? Well, across the resistor, it's pretty obvious. The voltage across the resistor is resistance times the current. And the current is this, I max times the sine of omega t plus phi 1. Okay, what about the voltage across the inductor? Well, voltage across an inductor depends on how fast the current is changing, because remember that a change in current changes the magnetic field within the inductor, which induces a voltage opposed to the change in the voltage. And this causes all kinds of things to happen, and the differential equation tells us what the solution would be if we just had an inductor. And we've seen all that. But it's going to be the inductance times the rate of change of the current. In other words, times I prime. And if we take the derivative of I, we're going to get an omega I max cosine of omega t plus phi 1. So we have this. And there's the omega, and there's the L. So that's very straightforward. Okay, now this is a little, the capacitor is a little more subtle, because as well, what's the voltage across the capacitor? Well, it's Q over C. Well, that was a good answer. It's a correct answer, and I'm glad people had it. That came out right away, so I'm fairly happy with that. That's okay, but we're not modeling this in terms of Q. We're modeling this in terms of the current. So what are you going to do in terms of the current? How do you know what the charge is in terms of the current? And somebody says, oh, well, you integrate, because the derivative of the charge is the rate of change at which the charge, the rate of change of the charge on the capacitor, and that's the current. So the charge is the integral of the current. Now, I'm being a little bit funny here. There should be a definite integral from some point. We can adjust the point, we can adjust our phase angles in such a way that we can ultimately just use the result of just now I'm looking for the adjective, because sometimes I lose words. The indefinite integral, that's the word I was looking for. I just used definite. You'd think I'd have indefinite in mind. Okay, so we're just going to use the indefinite integral and wave our hands a little bit right now, because we don't want to get hung up on those details. So if we integrate the current with respect to time, well, antiderivative of this is what? It's going to be a cosine, and it better be a negative cosine, so we end up with a positive derivative of the cosine. And reversing the chain rule, we're going to get a reciprocal omega. So it's very easy to see that this is an antiderivative of this, and it's the simplest possible antiderivative. And we're not including an integration constant. So there we have it. And the result is that our voltage across the capacitor is charge over capacitance. The charge as a function of T is this. So we just take this and we divide it by C and we get this. And that's very, very straightforward. Okay, well, those are our voltage drops. Well, that's simple enough. And it really is quite simple if you understand what an inductor does, what a capacitor does, and how you get the voltage in the capacitor and so forth. Which means, of course, since the total voltage drop across around the circuit is 0, that the EMF is equal to the sum of the voltage drops. So now we know what our EMF is here. And for some reason, I've got a cosine in one place and a sine in the other. It's not important because, of course, we can always get it with a phase angle, but let's just kind of, actually, no. I want that to be a cosine, never mind. Okay, so our EMF then is this, the sum of all our voltage drops. Of course, I factored out the I max, but everything else is just the sum of the voltage drops. This plus this plus this. Okay, and that's going to be our E max. And since I called it a cosine over here, we're going to call it a cosine over here. It doesn't really matter whether we call it a sine or a cosine because we haven't talked about the phase angle. And the phase angle for the sine is just going to be pi over 2 different than the phase angle for the cosine, either plus or minus a pi over 2. You can think that through. So that's a nice little package. We have this. Now we're going to talk a little bit more about the various parts of this.